Hi, in this tutorial, I will introduce an introduction to the convolutional neural network and how can we use it to classify a custom image dataset. To understand this video, you should be having a pre-required knowledge in deep neural network fundamentals and basic programming skills. The goal of this tutorial is to have an idea about the concept of convolutional neural network and to understand how to implement the CNN in the code. The content of this video is going to be as follows. First, we'll talk about image classification concept. Then we'll be talking about the CNN architecture. Then we'll be talking about the components of the convolutional neural network, and finally we'll have a sample code and we'll understand how can we implement the CNN in this code. So, what is image classification? In general, a classifier is used to identify to which a discrete set of categories and observation belongs. For example, classify an email to a spam or non-spam. But with image classification, we intend to take an image input and look at what class this image belongs, or in other words, we give the image a label which represents the output. So, for example, this is an image. We insert it to an algorithm, or we can say it's a function, and then we'll see the output to which label is this image belongs to. So we have three components: the input, output, and the function, which is an algorithm in this case. So why the output is equal to a function of x, the input? And this is what's called the supervised learning in the machine learning. So in supervised learning algorithm, the input is always labeled based on the model trained. To classify an image, we need an algorithm which can be a machine learning algorithm or a deep learning algorithm. And in this video, I will be talking about the CNN, which is one class of the deep learning or the deep neural network. So the deep learning as a classification approach is most commonly used to analyze visual imagery and are frequently working behind the scene in image classification. Why? This is because they're fast and they're efficient. But how do they work? So CNN looks like something like this. We can say this is the fundamental architecture for a convolutional neural network. And of course, in this video, I assume that you already have an idea about the neural network architecture in general. So we have the fully connected neural network, which is, I suppose, you already know. And here we're talking about the convolutional neural network. So the convolutional neural network CNN has an input layer and hidden layers and an output layer. The hidden layers itself contains of two stages. The first one is called the feature learning stage, and the second one is called the classification stage. In the feature learning stage, the image is going to be convolved progressively through the layers of the stage, and we can see that the name of the CNN convolutional neural network came from this process. The second set of layers which perform the classification process are fully connected layers with the same structure and performance as the normal fully connected neural network. So you may ask, what's the difference between the FNN and CNN? In fact, CNN is most commonly used than the FNN, and what makes them better than the FNN is that the CNN retain the 2D structure or nature of the image so that we don't lose its spatial structure. But in the case of the fully connected neural network, the image is going to be flattened and is going to be taken as a vector of its pixels. Like here, the image is presented as a vector of its pixels values and fed them to the input layer. So the 2D structure of the image is going to be lost. Additionally, the performance of the CNN is faster and more accurate than the fully connected neural network. And as I mentioned before, the CNN doesn't take an input image as flattened to pixels and fed to the neurons in the first layer like the FNN. Instead, the convolutional neural network keeps the spatial property of the image, which will be useful in the feature extracting for the image. And this is basically the purpose of the convolutional stage here, which is the feature extracting. So looking at the architecture of the convolutional neural network, it basically contains of this structure or architecture, the input, then the convolution. After this, we apply some nonlinear activation function, and then we apply the pooling. We will be talking about all of these things later in details, but now I want to give you a big picture about the architecture of the CNN. So we have the input, convolution, reload, pooling, and this is going to be repeated as long as we have convolution layers, and then we'll be having the fully connected layers, and then last thing is the output layer, and in our case is the classification layer. So quickly talking about the function of each layer, the convolutional layer apply a convolution operation to the input, then it passes the information onto the next layer, and the pooling combine the output of clusters of neuron into a single neuron in the next layer. But the fully connected layers connect every neuron in one layer to every neuron to the next layer, as we already know from the fully connected neural network. And to summarize all of these, the first thing is to start with the input layer, or the input image, sorry. Okay, then apply many different filters to it to create the feature maps. We'll be talking about this later. And then apply a ReLU function to increase the nonlinearity. Applies a pooling layer to each feature map. Then flatten the pooled image into one long vector. Then we input the vector into the fully connected layer or the fully connected artificial neural network, and we process the features through the network. The final fully connected layer provide a voting of the classes that we're after, and then the network is trained through the forward propagation and back propagation for many epochs. This repeats until we have a well-defined neural network with trained weights and feature detectors. Now let's talk about the basic building blocks of the CNN separately for better understanding. The first stage in the hidden layers, which is the convolution. The main purpose of the convolution step is to extract the features from an input image. So the convolutional layer is always the first step in the CNN. So this is the picture or a photo for the convolutional stage or layers. We have here the image. Okay, with the size 36 by 36. And then the convolution operation starts off after we insert or we fed the image into the first convolutional layer. And we can see here the convolution stage may contain many convolutional layers and pooling, which in this case max pooling. We can have many convolutional layers. So, but why do we have so many? In fact, the first convolution layer is responsible for capturing the low-level features such as edges, color, gradient, orientation, etc. With added layers, then later, the architecture adapts to the high-level features as well. So, giving us a network with which has the wholesome understanding of the image in the dataset. So, first of all, we have the input image, and then we have the feature detector, which is called also filter, or sometimes it's called kernel. Okay, and then the output is going to be a feature map. Okay, and in this case here we have 1, 2, 3, 4. We have 4 feature maps. Okay, so we take the filter and apply it pixel by pixel, pixel block by pixel block to the input image. In other words, we slide the filter through the whole image from top left to the bottom right. To see exactly how is this happening, we can look at the next photo. Okay, here we have the image, which represented by the green color, and the filter or the kernel is represented by the orange color. Okay, and the output, which is called the convol feature or the feature map, mostly called the feature map, is here. Okay, so this is the input image, and this is the applied kernel, and this is the output feature map. So what's the filter? Basically, the filter is an array of numbers, as we see here. The numbers 1 0 1 0 1 0 1 0 1. This is the numbers or the array which represent the filter, and it's basically represent the weights or the parameters of the layer. So we apply the filter from the top left to the bottom right, and the distance the filter travels over the image is called the stride. For example, the stride in this example is 1, which means that you are moving your filter over 1 pixel each time or at a time. So, looking at this gate picture, this is the first kernel, and then it moves 1 pixel over the image each time it moves 1 pixel, and in each position the filter multiplies the value in the filter with the original values in the pixel. For example, here the values 101 010 101 is going to be multiplied by the values of the original values in the picture where the kernel or the filter is applied. In this case, 1 multiplied by 1, 1 multiplied by 0, and so on. And the multiplications are then summed up, creating a single number which represent the numbers of the feature map. So if we started at the top left corner, okay, and this number is representative of the top left corner here in the feature map. So similarly, the second number here is going to be a result of the kernel or a filter multiplied by the second position of the kernel to the image, okay, and then we move our filter to the next position and repeat the process all around the image pixels, and then the array we will end up with is called the feature map, or the convolved feature. Sometimes it's also called activation map. The output, the feature map, is going to be with the size n by n by d, where n is given from this formula, and the d is the number of filters applied to the image. Okay, so let's have a look at all these parameters. The w is the input width of the image, or any input to the any convolutional layer, and k is the kernel size, p is the padding. Padding is actually is an operation where we extend the edges of the image to preserve the features at the edges of the image. And in this case we don't have any padding. And s finally is the number of stride. It is stride, and it's by default 1 unless we change it. And this is a visualization of the feature map and the size of the feature map. So this is the input image with 32 by 32 size. This is the kernel or filter, and this is the output, which represents the height and width, which is given by n, and the depth, which is given by d, the number of filters applied. And in our case, the input image is 32, the kernel size is 3, so the output or the feature map is going to be with the size 30 by 30, and the depth is going to be according to the number of filters. And applying more filters, this is going to be a better job for preserving the spatial relationship of the image. And during the training process, the network is going to learn the weights, which are the numbers of the array of the kernel, to get or to optimize the output of the network. So going back to the feature map, if we apply many filters, the output is going to be many convoluted or convolved feature maps, which is smaller than the original image, as we saw here. This is with the size 30 and this is with the size 32, but the output is going to be larger in the depth. So we can create many feature maps of or the output of the convolutional layer by applying different features, detectors, or filters with different values, of course. So what's the purpose of having many feature maps and applying more filters? The purpose is to get different results for the image. For example, sharpen or focus the image, or blur an image, and we can also do edge enhancement, edge detection, and more. And the primary purpose here is to find the features in our image and put them into the feature map, and also still as well reserve the spatial relationship between the pixels. That's the importance. That's so important, so that the pixels don't get all jumbled up. Now we'll move to talk about the ReLU layer, or sometimes it's called the activation function or the non-linearity function. And if you still remember, this layer or this function is applied right after the convolution operation, and it's actually applied to each value in the feature map. Okay, so for example, this is the feature map. Okay, the ReLU function or the activation function is going to be applied to every value in the this feature map. Okay, so what's the purpose of the activation function or the nonlinearity function? In fact, the real world data we want our CNN to learn will be nonlinear. So in reality, the image is behaving nonlinearity. So, but at the same time, the convolution we are already done is a linear operation. Okay. So we are applying the an activation function onto our feature map to increase the nonlinearity in the network, because as we said simply, the image itself is nonlinear. Okay, and convolution is a linear operation because all the operations done to the convolution, which we have already know, the multiplication and addition make it behave as a linear operation. So what ReLU actually do is simply removes the negative values from an activation map by setting them to 0. So if we have any negative value in the feature map, the ReLU function is going to set this negative value to 0, so we can get rid of all negative values in the feature map. There are actually other activation functions than ReLU, which are, for example, tanh and sigmoid, but ReLU, however, is a popular choice because it can train the network faster without any major penalty to generalization accuracy. So here we are visualizing the ReLU activation function. Okay, so any negative value is going to be set to 0. So it acts like a rectifier. That's why it's called rectified linear unit ReLU. So pixel by pixel operation that replace all negative values by 0, as we said. And here you can see this this image or this feature map before applying the ReLU function, and this is right after applying the ReLU function. We only have the positive values here, and all negative values are removed. Now the last thing we want to do after ReLU before going to the fully connected neural network or fully connected layers is called pooling. Okay, this is the pooling operation. With pooling, we actually it makes it possible to detect objects in an image, no matter where they are located, no matter the size or the location, and no matter what's the lighting or the number of spots. So we actually want the spatial variances and for sure the flexibility. The pooling operation progressively reduces the size of the input representation. Here is the feature map. Okay, it's going to be reduced to this size from 4x4 to 2x2. We have many kind or types of pooling. One of them is called max pool. Okay, so pooling helps to reduce the number of required parameters and the amount of computation required, and it also helps control overfitting. So what's overfitting? let's talk about overfitting a little bit. Basically, overfitting is a problem in machine learning and deep learning. And to understand the overfitting, I'll be giving an example here. So let's suppose we have a network and we are training our data set. Okay, for example, we have two data set, dog and cats. Okay, and for example, for the dog data set, all the dog data set in the training stage have the images of spots of the dogs with spots and dark eyes only. Okay, let's suppose all the data set we are training contains dogs with spots. Okay, so our network will believe that for an image to be classified as a dog, it must have spots and dark eyes. So if we test if we test our network or our data with the same training set, okay, the dog with spots, it will do an amazing job of classifying dogs correctly. Okay, but if our and this is in the case, okay, if our output is only dog. Okay, but if we have dog and cats as an output, okay, and then we present new images, okay, let's say for example Rottweiler or Husky, different kind of dogs without spots, then the network will probably wind up classifying both the Rottweiler and the Husky as cats. Why? Because in the training stage, okay, the network didn't recognize all these variation in the training dataset, in the dog dataset. Okay, so we can see this problem happening. So we can say overfitting model is the situation where any given model is performing well to the on the training data, okay, but performing the performance drops significantly over the test dataset. Okay, so for example here the error with the training dataset is going better and better, but with the test dataset is going to be worse and worse with the time goes. So for this step we take the feature map. Okay, we take the feature map, which is this here, and then we apply the pooling, and then the result is a pooled feature map, which is reduced in the dimensionality, and at the same time it preserves the spatial invariance. Okay, so the most common example of pooling is called max pooling. In max pooling, the input image is partitioned. Okay, it is partitioned into a set of areas that don't overlap. Likewise, the filter applying. The output of each area, we have here 4 areas. Okay, the output of each area are the maximum value. For example, in this area the max value is 6, so the output is 6, and here is 8. The max is 3 in this, and 4 in the last area. This makes a smaller size for with fewer parameters. So by taking the maximum value of the pixels, we are accounting for distortion, and if the feature rotates a little to the left or to the right or whatever, the pooled feature will be the same. Okay, this is here we are reducing the size of and the parameters, and at the same time this is great because it means that the model won't overfit on the information. We could also use average pooling or sum pooling, but they aren't common choices. Now let's go to the last step in before the fully connected layer, which is the flattening. So the flattening happening right before we go to the fully connected layer. We need to flatten the last convolutional output in order to feed it to the neurons into the first layer in the fully connected layers. So we flatten the pooled feature map into a sequential column of numbers, which is long vector, as it's indicated here in this red, inside this red circle. And this could be done in one line command in the PyTorch, as we will see later. So this allows the information to become the input to the input layer of an artificial neural network for further processing. Once we finish the convolutional stage, or it's called sometimes the feature learning stage, we are headed into the classification stage, or the fully connected layers. Okay, at this step we add an artificial neural network to our convolutional neural network. The fully connected means every neuron in the previous layer connects to every neuron in the next layer. So what's the purpose of this layer? In fact, to use the feature map from the output of the last convolutional layer, and to use it to classify the input image based on the training data. So from these old stage, the convolutional pooling and so on, we are getting the feature map, or we are extracting the feature from the image, and then in this stage, the fully connected layers, we are trying to classifying the image and give a label to the image, and this happening based on the training data. The further processing to the features in the classification stage is that the fully connected layers combine our features into more attributes. This will predict the classes with greater accuracy, and this combines features and attributes that can predict class better. At this step, the error is calculated from the output of the last classification layer, and then it is back propagated through the network, and the weights throughout all the networks and the feature detectors are adjusted to help optimizing the performance of the model. Then the process happens again and again and again up to the point we are getting the best performance, or the lower error from the output layer. Okay, so this is how our network trains on the data or the features and the weights and the parameters throughout all the network. So once the network has been trained, we can pass an image, and the neural network will be able to determine the image class probability for the image with great deal of certainty. And we see here we have the last layer, which represents the classes or of the whole or of our data set. So according to the trained model is going to be to predict the correct classification or class of the input image. Well, by this finished introducing the an introduction for the CNN, or convolutional neural network, and right now I will be explaining a code which will be defined CNN and all its component, and we'll be looking at the some data set, and we'll be looking at how the algorithm or the network is going to get or to classify our data set based on the trained model that we'll be getting at the end. So let's go to the code. So this is the code we are going to run the classification with convolutional neural network, I'm using the Google Google Colab or Google Collaboratory. But before that, let's have a look at our data set that we want to train and to test. So here the data set, we have the testing and the training data sets. For each, we have 5 classes of jewelry data set. We have bracelets, earrings, necklaces, nose ring, and rings. In each, we have 638 images in each class, or in each in each class. And if you look here, I was trying to have a variety of images, so we can have for example, the bracelets alone, the bracelets on the hands, and so on. So as well, I do some data augmentation to my data set. Data augmentation means that we need to increase our data set by performing some transformation to the image, for example, rotations, flipping, and cropping, and so on. So in the training data set, I have 630 images per class, and in the test data set, I have 270 images in each. Okay, so we need to make sure that the data set in the testing are totally different from the data set from the training data set. Okay, so let's go back to the code and see what's happening there. So I suppose that you have good basics in the programming. So we'll be looking at the code very fast. I'm not going to explain every single thing deeply. I'm going to go through the code and explain the most important lines or commands in the code. So we start off by importing the necessary packages, and of course, because we are using the Google Colab, we don't need to download all these packages. They are already they're already existing in the Google Colab. So as you see here, Torch, NumPy, OS, all these packages or libraries will be using it through the code. Okay, in this step, we are mounting the drive, okay, so that we can use the dataset from Google Drive. So I uploaded my dataset to Google Drive, because using Google Colab you can import your data from the Google Drive. Okay, so after that, we can see here we list the directory. We have 2 folders, the testing and training, and here we have some transformation of the data, like we have to resize all our data to be with the size 32 by 32. This is very important, because in the convolutional stage, we have to make sure, or even in the fully connected neural network, we have to make sure all data set with the same size. We do the same thing for training, validation, testing, and in this case, I'm using the testing data set as a validation and testing. This doesn't matter. So let's do here. So in this step, we are loading the data, okay, and here we are defining the number of classes. We are going to use this when we define our CNN. Okay, so the output of this step is to get the number of classes and what are these classes. The classes start with the 0, label 0, and 1, 2, 3, 4. So we have 5 classes. So let's take a look at what we have in the train. We have this information, data set, and so on, and what's the transformation we have done to our data set, resize, rotation, and so on. Okay, and here we are downloading, or we are loading, sorry, we are loading using the data loader module in the PyTorch. So by this step, we make sure we load our data set to Google Colab. Now we can see we print train dataset, validation dataset, and test dataset. We have 3,150 images in the train, and in validation and testing we have 1,350 images. Okay, the input size is set to the 3232, 3 because we have RGB images, so with 3 colors channels. Okay, and then we are defining our model. So defining the convolutional neural network, we use this class, okay, which with the name nn.module, or in the name net, and nn.module means that we have neural network. So here we are defining the convolutional layers. We have 3 layers, okay, and when defining the convolutional layer, we have to have 3 parameters. Those are the number of channels, okay, the number of kernels or filters, and the size of kernel or filter. Okay, then we define the pool with this function, or with this line, and then we have the fully connected layers. We have 2. Okay, the first one will take the input size, okay, which is the flattened from the last convolutional layer, and the second hidden layer, or the hidden layer, is 512, and the final output layer is with a number of classes, which are in this case 5. In this function we apply the ReLU, and then we apply the pool to the output of the ReLU, and for each convolutional layer. And here we are taking the last output from the last convolutional layer here, which is x here, which is returned from the function, and this will be flattened, okay, because we need to feed forward to the fully connected neural network, so we need to flatten with using this line. Okay, so then we apply the ReLU and to the fully connected layer, and then we apply the dropout. The dropout is a function where to enhance or to overcome the overfitting. Okay, then we apply the second fully connected layer, or the last layer in the fully connected layer. So here we have the model, okay, and then here we are training and validating the model. Okay, it's a long I'm not going to go into details. I'm just going to show you how is the result from this. In fact, we trained our model with 50 epochs. Okay, so here we have the output of each epoch, and in the last epoch, which is the 50 epoch, we have the accuracy of the training dataset 88%, and accuracy for the testing dataset with 56%. Well, I think it's better to go back to look at what was happening before we got this this output or this result. Okay, first we define the optimizer and the loss function. The optimizer is going to be the what we call in the back propagation in the back propagation stage, we need the optimizer, which will help to train the parameters, the weights, and the bias in the neurons. And we also define the loss function, okay, which is going to calculate the error from the output layer. And then here we are training and validating our model. So we start with setting up some settings so that we make sure our model is going to be trained well. So first we define the model, and then we set the train loss, train accuracy, valid loss, and valid accuracy to 0 to avoid any unwanted values in these variables. Okay, and then we apply for loop. So from the train data loader, we have the inputs and we have the labels. The input is going to be the image itself, okay? So then we send the input and labels to the device, which is GPU in this case, because we are using the Google Colab in order to be able to use the GPU, because in our device, in my device, I don't have GPU. Then we clean the existing gradient to make sure optimizers are 0 at first in the beginning of the training. Then we forward the images to the model, okay? So we compute the output of input using the model. Okay, so this is the model we defined before. We input an image, and when we get the output, then we compute the loss from the model, and from the error we are going to back propagate the gradients, okay, using the loss back propagate, meaning that we are back propagating the loss, so we optimize the weight in the model. Okay, this is done by the optimizer, and then we compute the total loss for the batch and add it to the train loss. I didn't talk about the batch before. Here we have to define the number of batches. Okay, where is it? I don't know, where did it go? Yeah, it's here, the batch size, meaning that the number of images in the train step, okay? For each train step, we are going to have a number of images. So the number of batch is 32. This means will be our image data set. For example, if we have 1000, it's going to be divided into 32 sets. So each set is going to be input to the model. Okay, let's go back. After computing the loss, we are computing the accuracy, okay, by using the prediction of the model. Later we do the same thing for the validation data set. So in the validation loop, we're going to send the input and labels to the device, and then forward pass the same, and then we compute the loss. Then we compute the total loss of the batch, and then calculating the accuracy. So the same thing is going to be done to the validation data set. The only difference, and the important difference here, is that with the validation data set, we are not going to back propagate the error through the model to train the parameters. This is done in the training only. Okay, here the back propagation is be doing to train. For this is for the purpose to train the model, but here we are not training the model, we are validating, or we can say testing, but testing is going to be the last thing. But here we validate, we need to see to what extent the model is going to give us the accuracy. Okay, so we calculate the accuracy and the loss of the validation. Later we are the final thing is to train the model and see the accuracy and loss for both training and validation. So as we saw before, the last epoch gives us 56.2% for the validation. This is the accuracy of our model. Okay, so here we can visualize or figure the loss and the accuracy of both. Okay, and then here we compute the test accuracy. With test accuracy meaning that we are given the model unseen data set, and then it predicts the output. So in this case we are giving the same validation and testing data set to the model to give us the prediction, and then calculate the accuracy. So here we are doing the same thing. Okay, last thing, we find the average test and loss for the test. Okay, here we are predicting the class of a single test image. Okay, we'll be using this in here. Okay, where we can test a single image. For example, this image. Okay, what is this? This is the nose ring, right? So I test this image to the model. Okay, here where it is saved in the drive, in my drive. Okay, and this is the path. Okay, and then we predict. This is the name of the image, and this is dataset is the path of the image, and we use the model to predict to what class this image belongs. Okay, so the first prediction was the nose ring. Okay, this was correct with the score 20, and it gives only 0.6 for necklace and 0.5 for earrings. So these are the probabilities of not the probability, but what we can say the confidence. Okay, so our model is confident that this photo or this image belongs to the nose ring class. Okay, which is very good, which gives 20, which is very good comparing to the other two predictions. So here we are computing the test accuracy. We are getting the last 0.56, which is 56% accuracy. So by this I end up this this tutorial by hoping that this was helpful for you. If you have anything to say, to tell me, just write a comment. Okay, thank you very much for watching this video.